Okay, YouTube, in this video we're going to continue our exploration of solving systems of nonlinear equations, but we're going to look at a unique situation in which our equation happens to be nonlinear, but also of the form ax squared plus by squared equals to some c constant here on both of our equations. And if both of our equations are of this form, then we actually can use not just the substitution method if we want, but we could use the addition method. Actually, I would prefer to use it if they're both in the similar forms, because then what our goal is to just eliminate a variable of one of those to bring it down to just one equation of one variable. So we say that in solving systems with two variables, we learn that the addition method works well when both the equations are of the form ax plus by equals c. It says for nonlinear systems, the addition method could be used when each equation, and it's got to be both of them, but both equations are of this form ax squared plus by squared equals c. And if necessary, we'll multiply either equation or both equations by appropriate numbers so that the coefficients of, say, either your x squared or your y squared term have a sum of 0. And what we'll do is then add those equations, and that will be a new equation, but in one variable. So that's our goal. And so what you're going to see here is a series of steps that I would suggest you go through in doing the addition method with nonlinear things. And remember that we're saying that we have equations of the form ax squared plus by squared equals c, but we say that write both of these in this form if necessary. That is to say that, this system that we see here, these two equations, we have an ellipse and a circle. And again, here's the neat thing about this. We're kind of starting knowing that we have 4 different solution pairs where these intersect. But what we want to do is solve this system. I would say that if the first equation could have looked like this, we could say if we were to put the x squared term on the right side, here would have been that equation. And so I guess the idea is that we would have needed to rewrite it the way it is looking now if it had not been in that form already. So now it is in that form already, so we're just going to run with this. But I would say check it out. If you were doing an addition method here, easily we could see that, check it out. If we took the second equation times a -1, we would get a negative y squared, and our y squares would cancel out. So let's rewrite this system. We have 4x squared plus y squared equals 13, and our second equation, after taking it times a -1, would be negative x squared minus y squared equals a -10. So basically, step 2 here said, if necessary, multiply either equation or both equations by appropriate numbers so that the sum of the x squared coefficients or the sum of the y squared coefficients is 0. You can see that by taking everything in the second equation, what we're going to do now in step 3 is add these together, but we've caused it so that those have a sum of 0. And so we would say 3x squared equals, over here adding these together, 3 on the right, looks like we get by dividing by 3 essentially. We're going to solve this now. We get x squared equals 1, and of course, if we take the square root of 1, here's the important bit of this whole problem right here. Essentially, what we find out is that taking the square root of both sides of this, we have to say that x is equal to plus or minus 1. So I'm going to put a box around this, but just to be clear on this one, I'm going to write solutions, solutions. And what I want to do is I want to point out that we get positive 1 for one of our x values, and we get negative 1 for one of our x values. So let's say graphically we hadn't had this picture on the right yet. I couldn't tell you that it had to have 4 solutions, maybe, right off the bat, but I do see that I get at least 2 x values here. And so what we traditionally do with x values, of course, go back and plug them into the equations and solve for y. So that's exactly what I'm going to do. And if both of these equations up here, I'm more inclined to take these and plug them back into the x squared plus y squared equals 10 equation, just because it's a little bit simpler. And so look what happens when we plug in for x. Let's go ahead and start with our positive 1. That's easy to work with here. Essentially, if we plug in a positive 1, 1 squared is 1, so we get 1 plus y squared is 10. Now when we subtract 1 from both sides, here's the thing. We get y squared equals 9. Let me scroll down here, and then of course, ooh, ran out of room. So we're going to take it over here. We say to the square root of 9 that we get for y. We get the square root of 9. But what this comes out to be is plus or minus 3. So in this unique case, what we're seeing is that when we plug in 1 for x, we don't just get a positive 3. We actually have to write this twice. We here get 1 gave us also negative 3. And so we could see that 1 goes to positive and negative 3. The same thing is going to happen, and this is crazy. When you plug in a negative 1 for our x value here, you see that we get the same thing, but only because you can see how this kind of gives us the same equation. When we square a negative 1, we get a 1. And so in this particular case, I'd say, I can see that y gives us plus or minus 3, but only when x equals negative 1 also. So we'd say 3, and this would be negative 1. Again, negative 1 gave us a positive 3, or sorry, a negative 3 as well. So we would see that these are the 4 solutions of our equation here. So what I'd like for you to do, of course, is to give it a shot here. What I'm going to do is load you up with another ellipse, okay? And these are actually two ellipses, not two circles, not a circle and an ellipse. So what I'm going to have you do is go solve this system now using the addition method. Cancel out your x's squared or your y squared. Make sure you're putting pluses or minuses when you're taking your roots. But also what I want you to do is then go into Desmos.com and graph both of these equations. Just type them in as you see them and use your caret key to put in your exponents. But basically, I want you to verify graphically the solutions that you get algebraically. Cheers.